Okay, so herein we are gonna keep going how to do analysis of electrostatics in PN junction diode. So let me see. Okay. So since we are going to use the depletion approximation as shown in here, the sharp edge at x of minus xp and at x of xn, the depletion layer has been well formed. Beyond this region, all the p-side n-side bulk regions are well neutralized so that the charge density rho is 0. So if I draw the charge density plot, rho versus x, plus charge can be found in the n-side because of the donors, ionized donors, and the negatively charged regions are found in the p-side because of the ionized acceptors. So with the Poisson's equation, we can write down this equation, I guess. This bar should be here. So the electric field dx is the electric constant of silicon and the charge density on the p side. So on the p side, charge density is minus q times n sub a. So by solving this first order differentiation, the electric field intensity as a function of x can be written like that, as we have done. And using boundary condition, what was it? So electric field at x of xn is 0. So using this boundary condition, we can get this equation. So this p should be here. No. Sorry about that. That is on the p side, so minus xp. And on the n side, we can repeat to solve the Poisson's equation of this. Epsilon silicon and inside the charge density here, q times n sub d. So using boundary condition at x is xn 0, then we can solve this first order differentiation and we're gonna get this electric field as shown in here. So I guess this bar should move down here. It's here. Okay, and xn. Some typo. All right. Then in the next lecture note, the thing that I would like to tell you is this. If I draw the electric field versus x, we're going to expect these two curves, xn here minus xp, 0. So previously I mentioned that in the game plan, in the previous movie clip, you have seen that the game plan for electrostatic analysis. So on the very bottom line, you may find out this sentence: the electric field across PN junction diode is continuous even at x of 0, even at the physical contact right here between P and N. The electric field is continuous. So let me see. So let me see. Yeah, let's do this. In the previous slide, when we estimate and derive the equation for electric field, that was written as blah blah blah. And from that equation, the slope in the n side, this part, has been determined as q times n sub d divided by epsilon silicon. What about this part? Here the slope was minus q n sub a divided by epsilon silicon. Since the electric field should be continuous at x of 0 here, so let me define that this value is electric field, but in terms of magnitude of electric field, this is maximum, so Emax has been used to denote this point. Then let's calculate the slope by using this value and that value. So I mean the Emax divided by XP is equal to Q times NA over epsilon silicon. Of course, I'm talking about the magnitude only, okay? And that equation is number 1. And another equation that I want to derive is this. So if I'm using the side length bar and height, I can write down the slope for this again. So Emax divided by Xn, only the magnitude is equal to Q times Nd over epsilon silicon. Okay, so now let's name it as equation number 2. So from 1 and 2, Emax should be the same for equation 1 and 2. Okay, so I mean that this Emax, that Emax should be same. So if I write down Emax from equation 1, Q and A, silicon XP, okay, and from here, from equation number 2, Emax is equal to Q and D epsilon silicon Xn. So this Emax, that Emax should be identical because at this point the electric field is continuous. So Q and A epsilon silicon XP is equal to what? This, okay? Q and D epsilon silicon Xn. So from this equation, Q is cancelled out, epsilon cancelled out. So Na Xp is equal to Nd Xn. Okay. So this condition can be found and derived. We're gonna use it later when we estimate the depletion layer width across PN diode. Okay, so let's keep going on and keep doing the electrostatic analysis. This part, this lecture note is on electrostatic potential. So from the electric field intensity, we are going to derive the electrostatic potential. So let's do that. Let's find out the electrostatic potential for each part in PN diode. In other words, on the P side, what is the electrostatic potential? And on the N side, what is the electrostatic potential? Okay, so the answer can be found here, Vx. Where does it come from? We have derived and have completed uh, equation for electric field intensity on the P side, right? So using this equation, we can derive the potential. How? dV dx is minus electric field. So plug in the equation into the E, and by solving this first order differential equation, we can derive the potential as a function of x. Okay, but since this is first order differentiation, so in the end, we're gonna have one unknown constant. So to know what this value is, we need one more boundary condition. But as I mentioned before, the potential value at x of minus xp at the edge of the depletion layer on the p side is defined as reference, grounded, 0. Okay, so we can use this boundary condition when solving this first order differentiation. So please do that by yourself. Then you're gonna derive this second order polynomial equation. And similarly, we can repeat this whole process for the n side. But in this case, definitely you should use an electric field equation on the n side and plug in this equation first order differential equation, and you need another boundary condition. What is it? Yes, at the edge of the depletion layer on the n side is equal to VBI. But here VBI is a constant, but we don't know the exact value. But as long as you know the doping concentration on the p side and n side, you may estimate this value. For example, if I write down it in equation KT over Q at Ni square n sub D plus KT over Q at Ni, no, not square Na. So in the end, built-in potential is defined as KT over Q at Ni square Na. So once you know the doping concentration on the p side and n side, since Ni is the intrinsic carrier concentration for silicon, that is 10 to the 10 per cubic centimeter at room temperature, and KT over Q is a 26 millivolt. So you can simply estimate the built-in potential value once you know those doping concentration values. Okay, so on the n side, you can estimate, derive the potential as a function of x, and this unknown constant can be well addressed once you're going to use this boundary condition. Then D2 has been removed and VBI has popped up in this equation. So on the p side, the potential, on the n side, the potential are well described mathematically, and now you can draw the potential versus x plot. Herein, one more condition that we are going to derive. What is it? Yeah, at x of 0, in the PN junction diode, at this interface at x of 0, the expressions for p side and n side must be equal. That means potential value at x is 0 is equal to this. So you know what that means. The potential value slightly at the on the p side, it should be identical to the potential value uh, at this interface, but slightly on the right hand side. So this equation should be satisfied. So from the equation that we have derived in the previous slide, just plug in instead of x, just plug in 0 value. Then you will get this equation, right? Minus Q and D to silicon. Yes, okay. So using this equation as well as using this condition that we have just derived, you can solve xn and xp. So xn, xp are variable, na and d is kind of constant, q we know, and d know. Dielectric constant we know, VBI we know once we know the doping concentration, right? So two unknowns and two equations, so we can solve it. Okay, so please do that by yourself, and the answer can be found out here, xn and xp. So we're almost done. Here in p side and n side. So here in x of 0. So using depletion approximation, the depletion layer has been widened up to plus xn down to minus xp. And here in this slide, we would like to know the depletion layer width. That means xn plus xp. So you notice that minus indicates, the left-hand side with respect to the interface. But here W means the magnitude of the total width of depletion layer. So we can simply use xp only. So just by summing those two values, we're gonna get the depletion layer width. Okay, right. In this slide, what if the uh, doping concentration on the p side is much heavier, higher than the doping concentration in the n side? So actually, we are talking about the one-sided p-n junction. Then this depletion layer width is governed by the doping concentration in the lightly doped side. Again, so go back to this equation and think about the P plus N side. So P plus means Na, N side is Nd. So Na is much higher than Nd. So in this equation, N 1 over Na, so this term can be much smaller than this term. So Nd is the key knob in determining the total depletion layer width. So in P plus N junction, all the depletion layers are actually formed on the lightly doped side, in this case, N side. Okay, so remember this. Whenever you are taking a look at the one-sided PN junction diode or in MOSFET, the depletion layer should always be found and formed in the lightly doped side. Okay. I guess this example is very simple, so I hope you can solve this problem set by yourself. So please do that, then you will get some number for a given doping concentration, uh, how much of built-in potential can be formed, and the depletion layer width is, that is 120 nanometer. Okay, for this doping concentration combination. So please solve by yourself. And this is the summary. And that's all for the lecture note. Thank you very much for your attention and see you in the next semester. Bye bye.